It was supposed to be just another telescope pass until the James Webb team spotted a trace chemical in the skies of a distant world. K2-18b, 8 times Earth's mass, blanketed by clouds, orbiting a quiet red star for trillions of years. And now, evidence, water vapor, methane, carbon dioxide, and something else, sulfur signatures almost never seen without life. When the models were run, the odds jumped off the page, a 99.8% probability. This planet's atmosphere isn't dead, but living. If these signals hold, the James Webb may have just found a 49-degree world where chemistry and biology merge, proof that we may not be alone. But how solid is this discovery, and what exactly did they see? Late at night, a notification pops up on the Cambridge team's Slack channel. A new batch of James Webb data has finished processing. Niku Madhusudan, the project's lead, scrolls through the spectra, each line a potential clue from a world 120 light-years away. Among the expected signals, one feature stands out. It's not water vapor, methane, or carbon dioxide. Those, by now, are familiar. This dip in the mid-infrared, persistent across the data, refuses to vanish no matter how the code is tweaked or which reduction pipeline is used. The team's first reaction is disbelief. Someone suggests a glitch. Another reruns the analysis using a different method. The anomaly survives. More hands join in, each scientist independently downloading raw files, running their own calibrations, stripping out instrument noise, testing every plausible source of error. Each time, the same spectral fingerprint appears. It lines up, almost perfectly, with dimethyl sulfide, a molecule that, on Earth, is almost exclusively produced by living organisms in the ocean. Slack messages pile up. There's a sense of euphoria, but also a careful, almost anxious focus. Mans Holmberg, working late at the Space Telescope Science Institute, describes watching the signal remain steady through wave after wave of robustness checks. The excitement is real, but so is the caution. Nobody wants to jump to conclusions. The team knows what's at stake. If the feature holds, it could mean biology on another world. But first, every possible explanation must be ruled out. The anomaly has survived the first round. Now, the real work begins. K2-18b circles a dim red star in the constellation. Leo 120 light-years from Earth. This planet is nearly 9 times heavier than our own, with a mass of about 8 Earths and a radius that stretches more than twice as wide. Its orbit is tight and quick, just 33 days to complete a year, hugging its star far closer than Mercury does the Sun. Gravity on K2-18b would press down with far more force than on Earth, shaping an atmosphere hundreds of times thicker than the one we breathe. The planet's host star is a quiet M-dwarf, a small, cool sun that glows with a steady, gentle light. Unlike our Sun, which will burn out in about 10 billion years, this red dwarf is built for endurance. Astronomers estimate it could shine for 1 trillion years or more, giving any orbiting worlds an evolutionary window vastly longer than Earth's. For life, time is everything. On K2-18b, the clock ticks slowly, offering billions, perhaps trillions, of years for chemistry to run its course. Tidal forces from the star likely keep one side of K2-18b facing the light at all times, locking day and night in a permanent embrace. Yet the thick hydrogen-rich atmosphere acts as a global blanket, redistributing heat and softening the contrast between the blazing day side and the frozen night. The result is a planet where energy flows steadily, and where the conditions for liquid water, so essential to life, may persist over immense stretches of time. In this system, the slow-burning star and its massive, tightly orbiting planet together create a stage where the story of life could unfold on a timescale unknown in our solar system. The James Webb Space Telescope operates nearly 1 million miles from Earth, stationed at the second Lagrange point, L2, a gravitational sweet spot where the Sun, Earth, and Moon balance each other. In this deep cold, Webb's enormous sun shield stretches out, blocking heat and stray light, letting its 6.5-meter segmented mirror focus on the faintest details in distant starlight. This mirror, more than twice the width of Hubble's, gathers far more photons, capturing signals invisible to previous telescopes. Webb's advantage lies in its ability to split starlight into thousands of precise wavelengths, reading the chemical story written in the atmosphere of a transiting planet. Every time K2-18b passes in front of its star, a tiny fraction of the star's light filters through the planet's air. Molecules in that atmosphere absorb specific colors, leaving behind a pattern, a spectral fingerprint unique to each compound. Transit spectroscopy, the method at the heart of this discovery, relies on catching these fingerprints with extraordinary sensitivity. Webb's mid-infrared instrument, or mirror-eye, is especially powerful here. It can detect subtle dips in light that would be drowned out by noise on other telescopes. Where Hubble might need 8 or more transits to reach a certain clarity, Webb achieves the same in just one, thanks to its larger mirror and advanced detectors. This technical leap means less uncertainty, more confidence. When the Cambridge team saw a persistent signal in the data, they knew it wasn't a fluke of the instrument or a trick of background noise. The hardware and methods behind Webb's observations set a new standard for reliability, opening the door to discoveries that once seemed out of reach. Every spectrum from K2-18b's atmosphere begins with a roll call of molecules. The most abundant is molecular hydrogen, H2, which shapes the entire character of the air. This lightweight gas makes up the bulk of the envelope, giving the planet its low density and thick extended atmosphere. Next comes water vapor, H2O, present in clear, measurable quantities. Its signature appears as broad absorption bands in the infrared, unmistakable even amid the noise. Methane, CH4, is also there, its spectral lines etched sharply in the data, especially in the mid-infrared. Carbon dioxide, CO2, rounds out the list of major detected gases. Each of these molecules absorbs at different wavelengths, and together they create a complex pattern that only a powerful instrument like Webb can resolve. But there is something missing. Ammonia, NH3, which is common in the atmospheres of gas giants like Jupiter and Saturn, is either absent or present at extremely low levels on K2-18b. The spectral regions where ammonia would appear remain flat, with no significant dips or features to suggest its presence. This scarcity stands out, especially given the abundance of hydrogen and methane. The identification of these gases comes from matching observed absorption features to laboratory spectra. Each molecule leaves a unique fingerprint: water vapor with its broad, deep troughs, methane with its intricate, spiky structure, carbon dioxide with its sharp, defined bands. The absence of ammonia is just as telling as the presence of the others, narrowing the possible chemical pathways at work in the planet's atmosphere. This molecular inventory is the product of careful, repeated analysis. Multiple teams, using independent software and reduction pipelines, have arrived at the same set of dominant gases. The result is a clear, consistent picture. K2-18b's air is dominated by hydrogen, laced with water vapor, methane, and carbon dioxide, but with little to no ammonia. The raw data sets the stage for deeper questions about chemistry, climate, and the possibility of life. The atmosphere of K2-18b is not just a list of gases, it is an active, restless system defined by ion balance. Hydrogen, the lightest molecule in the universe, dominates the air, making it far more expansive than anything on Earth. Mixed into this hydrogen envelope are water vapor, methane, and carbon dioxide, each absorbing heat at different wavelengths and each present in ratios that defy simple equilibrium. On Earth, similar combinations would not persist for long without something constantly stirring the chemical pot. Yet, on K2-18b, these gases remain, hinting at a process, possibly even metabolism, that keeps the atmosphere out of balance. This disequilibrium is not an accident. When methane and carbon dioxide coexist in large amounts, they should react and cancel each other out unless something keeps replenishing them. On our planet, life fills this role, locking the atmosphere in a state that would otherwise be impossible. The same logic applies to K2-18b. The persistent presence of these gases, especially in a hydrogen-rich world where ammonia is scarce, suggests an ongoing source, perhaps geological, perhaps biological. But whatever the source, it is powerful enough to maintain a steady chemical tension, a planetary tug-of-war that resists settling down. The result is a climate shaped by more than just sunlight. Hydrogen acts as an efficient greenhouse gas, trapping heat and smoothing out temperature extremes between the planet's eternal day and unending night. Models predict a global mean temperature in the range of 20 to 50 degrees Celsius, warm enough for liquid water to remain stable, but not so hot that chemistry grinds to a halt. Strong winds, driven by the redistribution of heat, sweep across the planet, mixing gases and energy in a perpetual cycle. In this world, balance is achieved not by stillness, but by constant dynamic imbalance, a signature that, on Earth, is inseparable from life itself. On K2-18b, the boundary between atmosphere and ocean isn't a sharp line. Instead, it is a seamless gradient, where air thickens and blends into water with depth, erasing the familiar concept of a surface. The upper layers are dominated by hydrogen gas, laced with water vapor, methane, and carbon dioxide. As pressure mounts, the air grows denser, and clouds form in bands, somewhere between mist and fog, stretching across the planet's horizon. Deeper still, the pressure climbs to hundreds, then thousands of times that at sea level on Earth. In this regime, water and hydrogen intermingle, and the distinction between gas and liquid begins to blur. At certain depths, temperatures and pressures force water into exotic states, first as warm, dense liquid, and then as supercritical fluid, a phase that is neither truly liquid nor gas, but something in between. On Earth, supercritical water only appears in specialized lab chambers or deep within the planet's crust. On K2-18b, it may stretch for thousands of kilometers, forming a vast hidden ocean beneath the clouds. There is no solid ground to anchor an ecosystem. Instead, potential habitats exist as layers suspended within this vertical column, each defined by its own pressure, temperature, and chemistry. The upper atmosphere could host airborne microbes, drifting in temperate cloud decks. Deeper down, where the hydrogen-rich air merges with a warm, watery sea, life might find refuge in high-pressure aquatic environments, feeding on chemical gradients or energy from the planet's interior. The possibility of a biosphere is not limited to a single zone, but could extend through the entire gradient, from the highest clouds to the deepest reaches of the global ocean. The planet's structure offers a canvas for life that is layered, dynamic, and unlike anything on Earth. Three distinct possibilities for life on K2-18b have captured the imagination of planetary scientists. The first centers on the planet's upper cloud layers, where temperatures and pressures may resemble those of Earth's lower atmosphere. In this band, microscopic organisms could drift on updrafts, feeding on chemicals in the air, much like bacteria and algae do in the cloud decks of Venus or the plankton swarms that seed Earth's oceans. Here, sunlight filters through the haze, providing energy for photosynthesis or chemical reactions, while droplets of water condense and evaporate in a slow cycle. Deeper in the gradient, where hydrogen-rich air merges with a superheated ocean, the chemistry changes. In these high-pressure waters, life might take root around hydrothermal vents, drawing energy from the planet's interior. On Earth, such environments teem with microbes that live without sunlight, thriving on hydrogen, methane, and minerals. On K2-18b, similar processes could drive entire ecosystems, perhaps even generating the gases that Webb's instruments detect far above. A third scenario envisions life that breathes hydrogen, not oxygen. Some Earth microbes already use hydrogen as a fuel, extracting energy from redox reactions that have nothing to do with air the way we know it. On a world dominated by hydrogen and methane, this kind of metabolism could be common. Each of these biospheres would leave a distinct chemical fingerprint, shaping the atmosphere in ways that telescopes might one day read as unmistakable signs of life. Eddie Schwieteman, an astrobiologist at UC Riverside, reviews the data with a practiced skepticism. For him, A 3 sigma result, about 99.7% confidence, remains a gray area. Impressive, but not enough to rewrite textbooks. The margin for error is thin. To test the signal, researchers run injection recovery experiments, adding synthetic dimethyl sulfide features into raw JWST data, then processing them through every available reduction pipeline. The question is simple. Can the pipelines reliably recover the DMS signal, or do they sometimes produce false positives when no real feature exists? Each round of analysis quantifies the detection rate, the amplitude recovered, and the risk of mistaking noise for chemistry. Sarah Hurst, a planetary chemist, pushes the search further. In her lab, she simulates hydrogen-rich atmospheres under M-dwarf light, searching for abiotic pathways that might explain the DMS without life. So far, no experiment has matched the concentration seen in K2-18b's spectra, but the gap between laboratory yields and planetary scale remains wide, and the possibility of unknown chemistry lingers. The scientific community knows what it would take to settle the question: more transits, deeper spectra, and new instruments. The Roman Space Telescope and ESA's aerial mission promise to expand the survey, while the extremely large telescope on Earth will sharpen the view. Each mission adds to the evidence, pushing the odds closer to certainty, or ruling out life's signature one molecule at a time. 3 out of every 4 stars in the Milky Way are red dwarfs, like the one hosting K2-18b. These small, steady suns burn for trillions of years, far longer than the 10 billion-year lifespan of our own. If life prefers time and stability, then most of the galaxy's habitable real estate lies around these ancient embers, not bright yellow stars. The discovery of a possible biosignature on a world orbiting such a star doesn't just hint at a single anomaly. It raises the possibility that life could be common, even routine, among the billions of planets circling red dwarfs. But the search for life now relies on more than telescopes and patient eyes. Machine learning algorithms, trained on vast libraries of simulated spectra, sift through mountains of data from missions like the James Webb Space Telescope. These systems flag subtle patterns, chemical ratios, rare molecular fingerprints that might escape human notice. In the coming surveys, artificial intelligence will become a partner in the hunt, mapping out planetary atmospheres at a speed and scale no team of scientists could match. With detection comes responsibility. International panels and policy groups are already debating how to protect the fragile possibility of alien biospheres. Proposals range from strict non-interference to the recognition of planetary rights, echoing the earliest debates about preserving life on Mars or Europa. The discovery of a living world around a red dwarf would not just transform science. It would force a reckoning with how humanity approaches the rest of the cosmos. K2-18b orbits a quiet red dwarf 120 light-years away, with James Webb Space Telescope spectra confirming a hydrogen-rich atmosphere, water vapor, methane, and carbon dioxide, while ammonia remains undetected. In September 2023, researchers reported a spectral feature consistent with dimethyl sulfide at a confidence level of approximately 3 sigma, a compound on Earth produced almost entirely by life. Yet, experts note that alternative chemical pathways and instrumental noise cannot be fully excluded. K2-18b's climate models indicate a stable, heat-balanced world with possible liquid water, but no direct evidence of organisms has been found. With M-dwarfs making up about 75% of the galaxy's stars, the implications for the prevalence of habitable worlds are profound. As new missions, like Ariel and the Roman Space Telescope, prepare for launch, and machine learning accelerates spectral analysis, scientists face both extraordinary promise and persistent uncertainty. The search now moves from asking if life exists elsewhere to rigorously comparing worlds, one spectrum, one atmosphere at a time.